Welcome to our first video this term, an introduction to groups. Well, you've already seen a lot of the material you need to know because you've studied binary operations. In fact, you've studied all of these things already. The key word you need to look at here is, well, words for all, for all, for all, for each. When you're demonstrating a set together with an operation forms a group, you must satisfy all these conditions, paying close attention to those words for all. And it's easy. We're going to look at this example, which is showing an operation table, also known as a Cayley table. The operation here is multiplication modulo 14. Let's remind ourselves what that means. Well, on an easy level, 2 times 2 is 4, 2 times 4 is 8, 2 times 6 is 12. Everyone knows that. Okay, that's easy. What does modulo 14 mean? It means when we do 2 times 8 to get 16, in this cell here, we wouldn't write 16, we would write 2. Because modulo 14, an easy way to think of that is the remainder when we divide 16 by 14. We get remainder 2. When we do this box, this cell, 2 times 10 is 20. The remainder is 6. In this one, 2 times 12 is 24. The remainder is 10. In fact, for this problem, it can be handy to write the multiples of 14 at the side. And we can continue in this cell. 6 times 4 is 24, so that's remainder 10. In this cell, 36, the remainder is 8. Can you pause the video for a moment and fill in the rest of the multiplication table? And I'll go make a cup of tea for a minute. Okay, you finished the table. You should have got these answers. I hope you did. Now, with these answers, we are able to progress to show that the set we started with, which was 2, 4, 6, 8, 10, 12, is a group. So we have to show it satisfies the requirements of closure, associativity, identity, and inverse. So here we go. First one, show that the set is closed under the operation. Now that simply means if I take any element in the set and combine it with any other element in the set, it's still in the set. The answer is still in the set. It doesn't go out of the set, hence the word closed. If you look very closely, all these numbers, they're all elements of this set, every single one. So the easiest way to justify that this set is closed under the operation multiplication modulo 14 is to say S with the operation multiplication is closed since all members of the Cayley table are in S. That's it. Okay, we're done with that. Associativity. Now, we get a free one here because this would be so complicated to check for every single permutation. Plus the fact that multiplication modulo n, where n is an integer, you're allowed to quote the fact that that is associative. You don't have to go and prove it individually. So you can say S with the operation is associative since multiplication modulo n is. You're allowed to quote that, you don't have to prove it. Okay, now it gets more interesting when we look at identity. Identity, remember, behaves like a 1 in multiplication that you learned when you're little kids. 5 times 1 is 5. 1 times pi is pi. It gives you the exact same answer when you combine an element with 1 using multiplication. 0 is the identity element for addition. So what's the identity element here? Does there exist a number in this set such that when you combine it with any element, it doesn't do anything? And furthermore, it works all the time for any element. Have a look at the table. You should be able to see it. Which of these elements is it to? Is it for 8 to 10? When you multiply, it does nothing. It has no effect. Can you see it? Yeah, it's 8. Look closely. 8. Eight is the identity element. Element. I'm going to make some mistakes in the video. Element. Okay, we're done. Last one, inverse. For each element in the set, there exists an inverse element which, when you combine it, it gives you the identity, which was 8. So let's just choose one at random. Here's 8. Okay, that means the inverse of 2 is 4. Now try not to be intimidated by the notation here. Usually 2 to the power minus 1 means something else, but you have to take that notation a bit more general. It always means an inverse. The inverse of 2 is 4, because when I combine them, I get the identity. And furthermore, it works the other way. It's commutative. Can you find the inverse of 6? The inverse of 6 is 6. It's what we call self-inverse. And what's the inverse of 4? I've forgotten that. It's 2. And what's the inverse of 8? It's self-inverse as well. And the inverse of 10? Yep, it's 12. And the inverse of 12 is 10. Okay. So you can say for each G in the set, G dashed exists in S as shown here. You've identified the inverse of each and every element. So we're done. We have shown each of these properties. Well, actually, we've shown these ones. We get this one for free. But don't forget to say it in order to be complete. And that's the process introducing how to show that a set is a group together with its binary operation using a Cayley table. Thanks for listening.